We've talked about parallelograms in a couple of previous videos. One of them we talked about the properties of a parallelogram, and we had 6 different properties about opposite sides being congruent, opposite angles being congruent. We had consecutive angles being supplementary. We had the diagonals splitting this thing in half. We had diagonals splitting each other in half. And we saw that if they were all right angles, that we had a rectangle. There were a bunch of different things we talked about with parallelograms. What I want to point out is that it splits our triangle, or rather our parallelogram, into 2 congruent triangles. So up here, if this was a true parallelogram, if I had sketched this a little better, the idea is that when I drop a diagonal in here, this diagonal line is going to split this whole parallelogram into 2 triangles that are exactly the same. They're rotated or flipped around in certain ways, but they are the same. They have the same 3 side lengths, the same 3 angle measures. They have the same area, same perimeter. All those things will be the same. What would be worth noting is that the area of a parallelogram here, so the area of the parallelogram we saw in our last video is just base times height. And many people know the area of a triangle pretty quickly. They'll or at least remember it very quickly. And they'll tell you, oh, the area of a triangle. So I'm just going to do a little triangle symbol here. Area of a triangle. They'll say, oh, it's 1/2 base times height. A lot of people will stop and go, well, why is that though? I don't know where that comes from. We've got all these other formulas that are pretty straightforward and easy to work with. This one's pretty easy to work with too. But it comes from this picture right here. We just said that this triangle here and this triangle here are going to be the same. Well, if the area of the whole parallelogram is base times height, then the area of one of these triangles is going to be half of the area of that whole parallelogram. So that's all it is. We have 1/2 base times height. And it will turn out that for any triangle, if you draw any triangle at all, you'll always be able to draw a parallelogram like this. So if I were to say, let's say we had a triangle that looks like this. So let's say this is our triangle here. What I can do is say, well, if I want the area of this triangle, it's actually the area of this parallelogram here that I've just drawn. It's the base times height situation again, cut in half. So I want the area of this guy, but I'm thinking of it as half the area of this parallelogram here. So if I know the base and the height, I know the whole thing's area, so we're just going to chop it in half to find the triangle's area, and that's all this is. So very briefly, if you had a triangle given to you, let's say it was something like this, pretending that that's drawn well. Heights are referred to as altitudes much of the time. They are always perpendicular to the opposite side from a vertex. So if I'd wanted to, I could have drawn the height from here over to here. It would feel weird. We're used to the height being oriented based on the bottom here. But as long as I gave you the length of this opposite side, you'd be good to go. So let's say the height was 10 and the base was 7. Then simply put, our area is 1/2, our base times our height. And you can think through this differently. You can either do 1/2 times 7 and then multiply by 10. But what I like to do is pick numbers very carefully. I'm going to do 1/2 times 10 and get 5. And then 7 times 5 is going to give me 35. That way I don't have to work with decimals at all. And I can get a very nice smooth answer there pretty quickly. So nothing crazy about working with these, but I just wanted to take a minute to kind of show visually why it was that the area of a triangle is 1/2 the base times the height.